So today we have Karyna Rodriguez. She will tell us about the bottom simulating reflectors black swan effect. It will happen just in a minute from now, and the talk will be about 35-40 minutes. And after that, we will have informal session among a handful of us. Announcement of the upcoming events. If you go to events.eag.org, you can see the full list of the sibling local chapters from different areas, Paris, Netherlands, Germany, and so on, as well as other events arranged by EAGE. One of the events coming in April is EAGE GeoTech Conference from 4 till 6 April. So anyone who is interested, registration is open. You can register there. Another event in May 4, Seismic 2022. It will be in Aberdeen, organized by a group of different associations and sponsors, including EAGE. So please take a note and join this conference. Then, as always, we're looking for speakers, and here we can see in the right bottom corner, we see that Karyna was giving a talk for us already in the past. It was back at Imperial, back when we were having our face-to-face meetings, which are hopefully coming back, and we hope to make them coming back to reality soon. If you're interested to give a presentation for us, or if you know someone who might be, please send us email or contact us via LinkedIn and announce that you're interested to give a talk. If you forget to renew your EAGE membership, please do so. And this webinar will be recorded, and therefore your microphones should be on mute. So Karyna, she's working for Searcher now, and she's a petroleum geoscientist with 30 years of multidisciplinary technical experience in global exploration inclined projects. She possesses diverse experience from her time at Pemex, British Gas, and other major oil companies, including regional seismic interpretation, prospect generation, amplitude anomaly, and sequence stratigraphy play analysis, integrated reservoir characterization, field studies, and prospect and volumetric chance evaluation, creating customized, systematic, probabilistic risk analysis processes, and working closely with high-level management to develop their strategic portfolios. She currently works at Searcher as part of a high-performing team dedicated to identifying, pursuing, and realizing new ventures to support efforts in optimizing exploration for oil and gas in mature and frontier basins around the globe. So I stop sharing. And Karyna, the stage is yours. You can start sharing your slides.
Thank you. Yes, and thank you for that introduction. I am just going to look for the presentation. And I hope you can see the presentation. Yes, I think I can see it on there.
Yes, we can see full screen.
That's good.
Yeah, very good. The sound is good.
I shall kick off. Yes, and thank you for the introduction. And can you see my cursor as well? My laser pointer? Well,
yes.
I assume you can. Yes, I can see you can. Okay. Yeah. Perfect. Yeah. So this presentation is going to be about bottom simulating reflectors. And hopefully towards the end of the presentation, you will see what I mean by the black swan effect and how interesting and fascinating actually these bottom simulating reflectors are, how much information we can actually extract out of them and how much they help us to understand, de-risk frontier areas because of where they are located. So just a short disclaimer and copyright that I have to show as part of this presentation. And to start with, because bottom simulating reflectors form the base of methane hydrate, of a methane hydrate zone, I want to just spend a couple of minutes explaining or talking about methane hydrate. So methane hydrate is this very interesting compound, which is made of methane in the center of a pentagonal dodecahedron structure surrounded by molecules of water, as you can see here. When you see it under the electron microscope, it's very interesting because it looks solid and at the same time it's got gas. So how does it form? Well, it forms, and I will explain why it forms in these environments, but it basically forms, it starts off by this slow seepage of, it can be thermogenic or biogenic methane from below. This methane can either accumulate in deposits below the seafloor, or it can travel up faults and you can get hydrate mounds on the seafloor. Or if you go to permafrost areas, you will also get this biogenic methane, which will be trapped again just below the surface of the surface. The reason why you get this methane hydrate deposited here is all explained in this phase diagram. In this phase diagram, we are really looking at the area here in gray. So on the y-axis, you have water depth and pressure, which are directly related. And then you have temperature on the x-axis. And you can see that this methane hydrate, which we are concerned with, the methane hydrate that is deposited just below here, the sea surface, forms under high pressure. So that would be quite deep water if we are talking hydrostatic pressure. So it's high pressure and relatively low temperatures, which is why it forms in deeper water and why it forms in permafrost regions. When you go along a geotherm, so if you just go along the same temperature and you move in depth, then you will see how temperature slightly increases, and we will get to a point at which methane hydrate in the solid form will no longer be stable, and it will transition to the methane gas phase. So this is what we are concerned with, and this is the two most important phases of the methane hydrate that I wanted to make you aware of, because this explains how we can use methane hydrate the way that we can use it, because the thickness of the zone will depend on the seafloor temperature, as you can see, the pressure, which is related to depth, and the geothermal gradient. So methane hydrate can be a drilling hazard, which is actually why it was avoided to begin with. So back in the days when they could see this reflector under the seabed, they weren't really sure what it was and they avoided it. And because it does, you can see by changing the pressure and temperature, it becomes unstable. It can suddenly become unstable and then give you a hazard. And this same hazard is because when it dissociates or when it changes very quickly, there is an induced instability. And so you might get submarine slumping, landslides, subsidence. Interestingly enough, it can also be used as an energy source. And the Japanese have come quite a long way in developing ways of carefully or in a controlled manner changing or extracting the methane out of the methane hydrate. But the most interesting application, and which is the one that I will be spending the rest of the presentation on, is how you can use it as a geothermal gradient proxy, and mainly in frontier basins, because as I explained, the low temperature and the high pressure, low temperature, will be mainly present in the deep water. How do you identify it on seismic? Well, methane hydrate, as I said, is the base of the BSR, a bottom simulating reflector, forms the base of the methane hydrate zone. And this is what we look for. We look for this bottom simulator reflector, or BSR, to identify where we might have methane hydrate. This will be a high amplitude event because of the acoustic impedance contrast of passing from the solid phase of the methane hydrate into the gas phase. It will be parallel to the seabed because, as I explained, as you increase the geothermal gradient, the methane hydrate will change phase to gas, and it will do so at the same thickness below the seabed. So you will get that change in phase parallel to the seabed. It's the opposite polarity to the seabed because it is a soft kick. And it's also cross-cut stratigraphy. As you can see here, we got stratigraphy going right through it, and this cross-cut stratigraphy. Here's another nice example of amplitude anomalies that we get in the free gas zone. And here you can see again that that cross-cutting stratigraphy and the same character as I showed you in the first section. A very common question that I get asked is if seismic velocity is different through this methane hydrate zone, and it will depend if methane hydrate is in pore space with above 40% porosity, then yes, there will be changes in velocity, but there are also ODP wells and DSDP wells that have gone through this zone where not a huge velocity increase has been observed. So you can get both. It's dependent on this porosity that is filling the pores. And one tip, when you flatten on the seabed, it's much easier to identify, especially when it's not exactly parallel to the seabed, or when you can see that cross-cutting stratigraphy much clearer when you flatten the seabed. So we have generated, because of what it depends on and because of where you find it, the thickness of the methane hydrate zone can actually be used as a proxy or to back calculate geothermal gradient. And for that, we develop a relationship from this graph, which was put together by a series of temperature pressure pairs from various methane hydrates that were encountered in different areas. You can see that Peru is labeled on here. 1988, leg 112 was the first well, ODP well, that was drilled into a methane hydrate zone. The reason being is that they didn't really see the methane hydrate very clearly on the seismic, and then they realized that they had gone through it, because up to that point, this methane hydrate had been avoided because we didn't know what it was, and there was a lot of worry as to what could happen. But then it was drilled, and after that, the first targeted leg, the first ODP leg that targeted investigating and understanding what was causing this BSR, was leg 164 in 1995 in Blake Ridge. But using this relationship, we have developed a geothermal gradient calculator using Excel, where you just have 4 inputs: water depth, the thickness of the BSR, the seafloor temperature, and the BSR section interval velocity. And you get the outputs that you require. So you will get the depth to the BSR depth converted to pressure. In this case, we include both hydrostatic and lithostatic pressure. Not everyone does that, and I've had various discussions with various people who use this methodology, and it seems that maybe this one seems to correlate better with well data. You get the temperature at the BSR, and therefore you get a geothermal gradient to the BSR. In this case, we had nearly 27 degrees centigrade per kilometer in this particular example. But there are other alternative calculations that you can use. They come from a couple of different publications. One is from Christophe Serry from Basin Research, and here is the formula that you can use. It's basically estimated from empirical gas hydrate stability law for seawater salinity and methane system. And by reading this publication, you can see how it's used and how it's calculated. In this case, it's only hydrostatic pressure that is taken into account. And then there's a simplified estimation, which assumes that you have a seawater methane mix, because of course you can have other types of gas hydrates, but we assume methane, a seabed temperature of 4 degrees, and then you've got this very simple calculation where it's just a couple of inputs, and the thickness will be in kilometers. And that comes from a publication by Neil Hodgson, my colleague, and myself in GeoExpro last year. So you can use any of these methodologies to back calculate and estimate the geothermal gradient. Then from the USGS, there was a map that was generated where they identified the gas hydrate where it was inferred and where it had been recovered. And really this tells you that there is a lot of gas hydrate all around most of the margins around the globe. And even some of these, we found gas hydrates that they didn't even predict that they would have gas hydrates, but a lot of them we have also confirmed. And here from our data library, our database, you can see that we have identified gas hydrates. We have in both our data library that we had in the past and the one that we've been growing recently. So I am going to show you some of these examples and what we found from the BSRs, what they helped us with in terms of de-risking the petroleum system or pointing us to interesting and maybe more academic topics that are interesting to discuss. So I'm going to start with offshore Peru, and I'm just going to spend again a minute just explaining the databases that we use to do our studies on BSRs. So we have here offshore Peru what we call a rectified data set, which includes all the seismic that you see in yellow here, which is about 50,000 kilometers of 2D, a lot of 3D seismic in the yellow polygons, and some wells as well. Now, this seismic data set we call rectified seismic data. Rectified seismic data is a series of different surveys, different vintages that are all merged together and are post-stack corrected for misties in time, phase, and amplitude. This is all loaded in a web-based platform, and then it's very easy to access via a subscription model, which makes it very easy and affordable. And we now have a very large data set, both onshore and offshore. You can see that we have now surpassed the million mark in terms of 2D offshore, and we've got nearly 500,000 of square kilometers 3D offshore. So what concerns us for this particular talk is the offshore data set that we have. And access to this data set has allowed us to do a very good analysis of the petroleum system in offshore Peru, and just finding very interesting aspects and surprising aspects of the geothermal gradient in this area. There had been some work done on the methane hydrate offshore Peru. Like I said, ODP 688 drilled in 1988, where they recovered some methane hydrate. Like I said, this was by serendipity. They went through it without meaning to go through it, but then this was a breakthrough and allowed us to gain good understanding of these BSRs. Also, some work that was done by Peru Petro, by Isabel Calderon and Jerome Caus on the various double BSRs that you see here, multiple BSRs, and their explanation of why you get this multiple BSRs, and some of them just being like legacy BSRs just left from previous methane hydrate zones. And very similar features that you can see here in the Trujillo Basin, offshore Peru. So the Trujillo Basin is just here in the southern part. Now, this area up in the Tumbes Basin has got a lot more exploration. There's production there as well. But down here in the Trujillo Basin, it's very much unexplored, with only a handful of wells drilled in the whole of this area. Being a 4-arc basin, not too much of a surprise. So looking at using this data set, using this rectified data set, which provides very large regional coverage, we were able to go into the Trujillo Basin and identify, I hope you can see, it's not as clear as other BSRs, but you can see this BSR right here. It's a bottom simulating reflector. You see that it changes in thickness, which is interesting in itself because it's indicating that there is a slight variation in geothermal gradient. So at this point, we use the calculator to calculate the geothermal gradient at this point and try to understand what we were looking at here. And you can see from the calculator that we estimated about 25 degrees centigrade. We weren't surprised. This is a 4-arc basin. We expect a relatively low on the low end geothermal gradient. There's a well up here, and this is got oil and gas shows. It's up on the high. But you can see here that with this geothermal gradient and 3.3 seconds of sediment, we infer that there's a source rock, the Redondo Formation, Upper Cretaceous source rock here. And that is probably generating hydrocarbons, which is probably providing the oil and gas shows here, but more likely, maybe providing some hydrocarbons to the nearby turbidites that are in the basin. And we know that this is becoming a very popular way of a very popular play type, or very successful play type as we've seen by recent discoveries. So that was 25 degrees centigrade. However, when you look at the BSRs that are present all along the margin, first of all, the ODP well, that had an estimate of 47 degrees centigrade per kilometer, which we thought might be an anomaly or might be a mistake. So what we did is we undertook to estimating and calculating the geothermal gradient for all the BSRs that we could see. And here are some examples of the BSRs that we could see, including this one, which you can see from the legacy and reprocessed data set, how the image improved to really make this BSR stand out very clearly and give us confidence that we do have methane hydrate here. So we back calculated the geothermal gradient, and surprise, total surprise, 47 degrees centigrade, 49, 43, 46, very high geothermal gradients for a 4-arc basin. So this is very puzzling, but in a way it also explains why you get these oil seeps that are well known in offshore Peru. The reason why this might be happening is because we've got a relatively young oceanic crust subducting here, which may not have lost all its radiogenic heat, or which may still be providing enough heat to have these high geothermal gradients. The great news, we don't need much overburden for our source rock to be generating hydrocarbons. And this is very likely to be coming from the hydrocarbon that is being generated by the source rock. So if that is the case, then we also looked for we looked for plate types that could be of interest in the offshore. We know that there are strong conturite currents. There's a Humboldt conturite system present day. So what we did is we used this data set to try to see if we could identify any evidence of conturite currents in the past. And lo and behold, here we have, well, there's a BSR here, and you see this features right here. We've got an analog. We've got a couple of analogs, the Coral Field offshore Mozambique with 80 TCF accumulation, migrating channels with this interaction between conturite and turbidites. Turbidites coming down the slope, conturites, which are orthogonal to that, taking away the fine-grained material, so the current is coming in this direction, taking away the fine-grained material, and the channel migrating opposite to the current. And we see that exact same character right here with this conturite drifts, the channels, and even some amplitude anomalies here. The source rock, we know high geothermal gradient, potentially generating hydrocarbons. So we could have this very prolific plate type out here in the Trujillo Basin offshore Peru. So really exciting. We published this on BSR, and I just wanted to share some of the discussions that actually happened on LinkedIn, because I thought they were very interesting, some of the feedback that we got. And for example, here from Brent Jackson, well, he said, if you actually converted this to depth, I think this is an accumulation. And exactly, he was exactly spot on, because when you compensate for water depth here, you can see how this is actually a closure. And you've got the amplitude, which is conformant with that structure, or it's related to the structure. And so this is an accumulation that is in a reservoir and is trapped by this structure. And then he asked about the geothermal gradient, and I said 40. And then he was like, oh, that explains why we have generation offshore Peru. We are generating hydrocarbon. And then we have Jerome Calves, who has done a lot of work in the area, and he thought that this was probably thermogenic gas being generated, and that it indicated that it was coming up the faults. And so we thought that was interesting. And then we thought Kiko Valencia, who has done a lot of work in the area and believes that this is an indication that we have a lot of potential here. So some really interesting conversations that happened on LinkedIn. I think it's a great platform for getting this sort of dialogue going. And I just wanted to share that with you. But now I'm going to move down to Brazil in the Pelotas Basin, where we have another world-class BSR. This BSR can be mapped over 100,000 square kilometers. So there is a lot of methane being generated in this system. Now, is it biogenic? Is it thermogenic? We have some oil seeps at the end of the BSR, which indicate that it's more likely to be thermogenic, because we wouldn't have light oil seeps on the sea surface if we didn't have oil being generated. Now, this section is in depth. And I think here you can see that due to the loading of the sediment, and also due to the cold oceanic dense dense cold oceanic crust being in this area, the colder and older and denser oceanic crust in this right here. We have differential loading and differential subsidence, which gives us these huge stratigraphic traps in the Cretaceous, which are pinching out to sea up-dip, reducing therefore the risk for up-dip CO. Just above the source rock. Now, we've been talking, Neil Hodgson and my colleague and myself have been talking about this Aptian source rock for about 8 years. And today, precisely today, there were some great news, very exciting news. I woke up to some of the best news I've woken up to for a long time. And it was that the Venus well has actually proven this source rock. Very interesting. When we calculated the geothermal gradient here in the Pelotas Basin, this is a map of the final geothermal gradient. You can see that there's very little variation. I mean, we plotted all these points. These are isotherms. So this is the hydrate thickness. This is the BSR depth. And these are isotherms, so different geothermal gradients plotted on here. Geotherms, sorry. And we plotted all the points of the BSR calculation of the geothermal gradient. And you can see that there's very little variation, despite the fact that we are going from continental crust out onto oceanic crust. And we have actually very similar conditions to the Venus well, very similar depth to objective, very similar water depths. And the fact that there was light oil means that we have the right geothermal gradient to be generating oil out in that oceanic crust. So here, 28 to 30 degrees centigrade, more or less, it stays without change despite being on top of oceanic crust. So we're learning a lot about these geothermal gradients that we had an idea, and I think the data is telling us differently. So if we assume that this geothermal gradient changes linearly with depth, but more likely this geothermal gradient will decrease with depth, but it won't be a linear relationship, then what we get in the most likely case is that we will be generating oil at around this temperatures at around this depth. And you can see here our oil generation is colored, predicted oil generation is colored in green. And there are some blocks that are in the open ground where we think, we predict, we model that we will be generating oil. So you can see all the use of this geothermal gradient. But the most exciting thing is, if I'd given you this presentation yesterday, I would have said source rock not proven. Today, I can tell you the source rock has been proven. And therefore, we have one less thing to worry about, two less things to worry about, because I'm giving you the maturity modeling as well with the BSR. Okay, so moving on to Mexico. And in Mexico, we can also see in the deeper water on our data, we can see this beautiful BSR right here. We have oil seeps. Now, there we know that the Tithonian source rock is working. So we can more or less guarantee that this BSR has a thermogenic origin. But we are using the BSR to tell us that there is a working hydrocarbon system, and together with the oil seeps. And then I don't know if you can see this very interesting feature right here that looks a little bit like there's an unconformity here. This is unlapping. These events are unlapping onto this feature, and it looks a little bit more lower amplitude and more transparent. So this is an interesting one, because for a long time, the channels have been well studied or well understood offshore Mexico, even the Cañonero well, which was drilled in a channel. So there is good understanding of this channel systems. However, there is one element that hadn't really been taken into account, and that is contourite currents. And what we see in this system, in a zoom in and in another area, is a very clear contourite drift. Now, this is a mega contourite drift because it's got 2 kilometers thick, about 20 kilometers across. And here you can see the channels migrating against the contourite drift. Amplitude anomalies, soft kicks, interesting. But the most interesting one is this soft kick right below the contourite drift. This soft kick we have interpreted as a turbidite, which has been trapped with hydrocarbon-bearing turbidite, which has the top seal as this fine-grained contract drift, which is the most common characteristic of this contract drift being fine-grained. And again, we go back to the Coral and Mamba field and we look at the seismic character, very similar seismic character, and very exciting plate type. So yes, these BSRs and hybrid turbidite contract systems are quite closely related because they're both found in deep water. But we find that relationship. Now moving on to Nova Scotia, to the north, still in the Americas. Very interesting in Nova Scotia. These are the 3Ds that we have both on the shelf, slope, and then out into the basin. What we found is that some of these 3Ds have example PDFs in DMC. So you can go into the DMC database and you'll see that they have some PDFs for some of these 3Ds. It's a great database. They also have data on the Weymouth well and the Aspy well. And these two wells are drilled through a salt canopy. So what Nova Scotia provides is a great opportunity to see what the BSR is telling us in a salt basin, because we have these BSRs in this Shelbourne 3D. So these are the BSRs that we can see very clear. Again, they've got that cross-cutting character, the high amplitude anomaly, the gas, the free gas anomalies below the BSR. They are simulating the bottom. They are bottom simulating reflectors. But let's look at the difference between a BSR that is above a salt diapier. So you can see here the thickness of the BSR. We calculated the geothermal gradient, and that geothermal gradient is at the high end, about 70 degrees centigrade per kilometer. So very high geothermal gradient for the area above the diapier. And what happens when you go away from the diapier? You can see how that BSR thickness increases from 242 meters to about 412 meters. Now with no diapier, we are up in the 40 degrees centigrade, around there. So there is a very important change because of the salt in that geothermal gradient above the salt and away from the salt. What happens below the salt is something different, but we're looking above the salt. So using that, what we found is that this would be your 90-degree isotherm oil window if you just assume that, if you just ignore the effect of the diapier and you don't take that into account. But using the BSR, it's very clear that there's a very strong effect. And this is what happens to your isotherm, to the 90-degree centigrade isotherm, when you take into account the effect going away from the salt diapier. So you can see that wherever your source rock is, it's going to be a very different model if you don't take that into account, the salt effect, or if you do. And what happens below the salt? Well, that's different, because we can see from the Weymouth well here, the data from the Weymouth well, that we first start off with this 28 degrees centigrade per kilometer above the salt. And then going through the salt, it decreases right down to 12 degrees centigrade and then picks up again coming out of the salt. So sometimes you have a lower temperature, like in the Santos Basin, if you've got very thick salt diapiers. And that's why you have actually oil in the Santos Basin in Brazil. But this area comes from here. And when we integrated with seeps, with oil seeps from at the sea surface, we can see that there are plenty of oil seeps in this area of the Shelbourne 3D. Interestingly, up on the shelf here, we have a proven gas system with TCFs which have been produced, and incredibly, over 1.5 TCF undeveloped discoveries. And I say incredibly because I think this area is being left behind with a huge resource left behind. Well, that was until today. Unfortunately, we heard about the invasion of Ukraine, and I think that made Canada change its mind about the LNG and about its policy. So gas could be again coming into the spotlight. These are advantage hydrocarbons. So we have proven petroleum system everywhere. And the Aspy well, look at this oil that was found in the Aspy well. Fluorescence in the cuttings, very clear evidence of oil, not in their objective, but definitely evidence of oil. So all this put together tells us that we have a very interesting petroleum system that we just need to understand better where the potential is. Going to South Africa, now we move over into Africa. I just want to show you that here the BSR is just confirming what the Bruprada well found. The Bruprada well found oil, mature source rock at this depth, which means that we probably have about a 50 degrees centigrade per kilometer geothermal gradient when we get to the objective, when we get to the discovery, the Bruprada discoveries, Bruprada discoveries from the Paravisi Play Fairway. And that was unexpected, or maybe not so much unexpected, because when you look at the BSR here, it's a very subtle BSR, but you can just about see the free gas anomalies below that very subtle bottom simulating reflector. And when we calculate the geothermal gradient based on the thickness, it comes out to about 50 degrees centigrade. So if Total did their homework, which they probably did, then they probably knew that this was going to be a high geothermal gradient. So I'm just showing you that there is calibration with discoveries, with ODP wells, and with basin analysis, that this methodology does work. Now I'm going to move to Oman, and Oman offshore in the Gulf of Oman. It's a very crazy geology. We have just gotten an agreement on this data set, and we were very surprised and shocked to see the geology here. It's quite complicated, but basically you have compression, which is happening up until the Miocene. And then after that, you get this extensional gravity slides when you start subducting over in the Macran, where the Macran subduction starts. This whole place gets tilted, and then you get this extension at the same time as you're getting compression, which is a bit crazy. And some of the compressional structures are caught up in this extensional area, and you get amplitude anomalies associated with that. But interestingly, at the end of the toe thrust, you get some simpler structures with DHIs. And then as we get into the Macran accretionary prism, this is where I want to go to, because we are talking about BSRs. You can see that very clear BSR there. So using the BSRs here offshore Oman, and this is a reprocessed seismic section where, again, you can see that BSR, back calculate the geothermal gradient, we map it where we can see it, and it varies between 20 to 40 degrees centigrade. Now, when you have a BSR, it's telling you that you have methane hydrate in the system. So there is a source rock, and what I forgot to mention, sorry, is that you have a complete section, a Jurassic, full stratigraphic section from the Jurassic onwards. You probably have a source rock down here, which is generating the hydrocarbons. And we see here that in the accretionary prism, lower geothermal gradient and then higher geothermal gradient away from that. So this would be very helpful to model where the source rock is generating and what phase of hydrocarbons. And the DHIs tell us that there is definitely hydrocarbon being generated here. So surprise. One more example, PNG. And you're probably wondering, well, what does she mean by black swan effect? So we are nearly there. I know that it's at the end of the presentation, but we are nearly there. So PNG has some beautiful BSRs. Again, you can see textbook type BSRs, reverse polarity to the seabed, high amplitude, cross-cutting stratigraphy, simulating the sea bottom. So beautiful BSRs here. Again, more characteristics. You've got the BSR, you've got high reflectivity, you've got free gas, and you've got the low reflectivity hydrates. So what could go wrong? Well, very clear BSR. Again, here we have, it's more subtle, but when you follow it around, you know that this is a BSR. But what happens when we go outboard of here? And this is crazy. This is the BSR reflector, and what happens to it is something we had not seen anywhere else in the world, that just took us by surprise, that just made us come up with all these different ideas as to what it could be. Were we really following a BSR? What is going on here? What is actually happening? That this BSR just seems to go right down, and we've never seen this behavior anywhere else in the world. So again, we posted this on LinkedIn, and I love it because people come up with all sorts of different ideas, or they say they've seen this somewhere else, and the discussion just got really heated and really interesting. And Keith Maynard was coming up with some nice ideas of he'd seen this before, and was it due to pressure changes? And the discussion just got going, and Keith said, well, he had seen this offshore Gabon. And then we just talked about how this feature was just, that there were some questions about, is it Schweizite? Is it an artifact? Is it a fault? And we just had to come back and every time say no. And then somebody asked the right question, and they said, oh, well, let's hope there will be 3D one day. There will be 3D data over this BSR one day. And guess what? There was 3D data, but it was just the way that we wanted to get the discussion going. And on this 3D data set, again, you can see that BSR acting in the weirdest of ways. And we know it's a BSR because we can track it from where it clearly is. I showed you the textbook example to this area, and we can just follow it, and we know that this is a BSR. So somebody, Hans Ledegaard, came back with some very spot-on observations, just confirming that this is a BSR because it has all the right characteristics. But what is going on? Why is it behaving in this way? So there is this one line that I think explains it very nicely. So this is an AVO display. This is an AVO display, and this is a carbonate reef. You can see this carbonate atoll or carbonate feature coming right up to the sea surface. And you can see how the BSR just bends as it gets close to the carbonate feature. And what we think is happening here is that this is this is what I meant by black swans. And I'll because black swans are just something that appear to be anomalies, but actually change the paradigm. And what's happening, what we think is happening here is that this is not simulating the bottom because there's very high thermal conductivity associated with the carbonates relative to the clastics. So maybe the heat is just being absorbed by the carbonate reef that reached the surface. But we mapped this spectacular BSR on 2D, 3D, and we found that the geothermal gradient decreases from 30 degrees to 15 degrees centigrade around the carbonate reefs. So it is these carbonate reefs that are creating this black swan. It was Nassim Taleb who writes about black swans as events that appear to be anomalies, but actually change the paradigms. And this is our BSR black swan. So, and actually, the reason why I put it on here, it's not because I was trying to be funny, but just because the shape of it is actually very similar to the black swan. That was not on purpose. So just to finish off, methane hydrate has a lot of applications. It's first of all a DHI because it's telling us that there is methane in the system. There is hydrocarbon generation. We just need to sometimes work out whether it's thermogenic, biogenic, but there's definitely methane in the system. And you've got potential in the free gas zone. And we saw that offshore Peru with that accumulation, that very clear structure-related anomaly. When you integrate it with seep studies, like I showed you, for example, offshore Nova Scotia, this can indicate oil generation. There's very clear oil generation, and there's no clearer evidence than this fluorescence in the cuttings from the ASPI-1 well that oil is being generated. It's just where are the accumulations? And sometimes it takes a few years, like in Namibia, to find them. It can help us to calculate geothermal gradients in frontier basins. It's a reasonable proxy, and this is confirmed by well data, by basin modeling. I showed you a lot of the ways in which we have calibrated this, and it helps us to de-risk source rock maturity, sometimes source rock presence as well. And offshore Peru is a beautiful example of that. We have a 4-arc basin with a high geothermal gradient. Now we can put that source rock into the oil window, and we have this prolific hybrid turbidite system. We have the black swan effect, of course, breaking paradigms. Not all BSRs, not all bottom simulating reflectors are bottom simulating reflectors. And just on a future note, it could be a source of energy. Japanese are working hard on that. And with that, I thank you very much. And I'm very happy to have a discussion, hopefully as heated as those on LinkedIn. Thank you.